back. All right, so now let's look at capacitors. Moving on to 15.5. Capacitors end up being really important in terms of our chapters on circuitry, so you're going to see these quite a few times. So we're going to go through it in quite a bit of detail so you can understand the mechanisms behind how capacitors work, because we're going to build on this. So although the building will come a little bit later in the class. So what a capacitor is if you have two uniformly charged metal discs very close with charge minus Q and plus Q. So we've got, they could be on either side, but minus Q and then plus Q. These Q's are going to be typically equal in magnitude, and you'll often see them using those conventions, blue for minus and red for the positive side. And they'll be separated by some S. And S is the distance between the discs, and then big R is the radius. All right, so this is a capacitor. Now, something just to note, a true metal disc can never truly have uniform charge because those electrons are going to go to the surface. Insulating discs are more likely to have a uniform charge, and capacitors are made out of both. But this approximation is good enough. So this is one of those things where we're approximating this, but just know that in the physical reality, it's a little bit off, but the calculations work out well enough. But if you're doing something precise, you'd need to take that into account. All right, so also what's true in a capacitor is that S is much, much smaller than R. And the attraction, so we've got a negative and a positive, so that are going to be attracted to each other, does keep the charge more uniform. So in terms of the calculations, we can safely assume uniformity. All right, so let's look at how to calculate this field. And we're going to do the same method we've been doing all along. So step one, we're going to cut it up and conquer it. I mean, physics is epic after all. All right, so we know how to calculate the charge of a disk, so we can use this. We're going to look at three spots, and we're going to use the pieces to just be our disks. So we've got our negatively charged disk over here, got our positively charged disk right here. We're going to look at the field in three different locations. So these are our two pieces, but we want to think about the field in locations 1, 2, and 3. All right, so so at locations 1 and 3, let's think about those first. So at location 1, we are going to have, and in each case we want to look at what the net field is going to be doing. So from the positive disk, we're going to have a smaller field that's going to be radiating away from the positive disk. And then we're going to have a larger field that's going to be pointing towards the negative. And our net field is in this direction. So our net field will be going in the right. Now let's look at location 3. So once again, let's see, we've got our negative field, which it'll be smaller and pointing in the direction of the negative disk, and then we've got our positive field, which is going to be radiating out, and it's going to be bigger. And so our net field, once again, is going to be pointing to the right. Now at location 2, let's think about this. So we've got our negative field, which is going to be pointing towards the negative. We've got the positive field, which is going to be pointing away from the positive, which means we're going to have a nice big old net field that is pointing to the left. Okay. So now that we know kind of what this is going to look like, let's start doing some calculations. All right, so we are going to be working, now we'll move on to step 2. We've drawn our fields. We're going to be working in Z. We're going to put the origin at the surface of the left plate. And Z runs to the right. And the locations of the pieces are Z equals 0 and Z equals S. So in terms of drawing this, so this is Z equals 0 and Z equals S. Yeah? Okay, so and if we want to look at the field, at location 2, so that's in the middle. It's going to be at Z for the left plate and S minus Z for the right plate. And our delta Q's plus Q and minus Q. And the assumption is that we're going to have a uniform charge density on inner surface. Okay, so we're going to use area is equal to pi r squared, which is the area of one disk. And now let's look at the contribution of each piece. So from the minus side, it's going to be approximately Q over A divided by 2 epsilon naught, 1 minus Z over R to the left. And for E plus, it's going to be Q over A divided by 2 epsilon naught, 1 minus S minus Z over R, also to the left. Okay, so now that we've got our fields for our two pieces, let's go ahead and add them up. This is not an integral, so everybody can do this. So our electric field at 2 is approximately Q over A divided by 2 epsilon naught, 1 minus Z over R plus Q over A over 2 epsilon naught times 1 minus S minus Z over R, which is approximately Q over A 2 epsilon naught 1 minus Z over R plus 1 minus Z over R. And moving along, this becomes approximately Q over A over epsilon naught 1 minus S over 2 over R. Now remember, I said that S was much, much smaller than R. So we've got really small on top and really big on bottom, which means this becomes approximately Q over A divided by epsilon naught. And the field is fairly uniform between the two plates. And so we can see this is actually just 2 times that of one plate. So remember that the field of a plate is approximately Q over A over 2 epsilon naught. So this would be consistent with what you might imagine. And there's no Z dependence, which indicates the uniformity. So again, our concepts are working out. So now let's look at locations 3 and 1. So for both of these, E points to the right. So in this case, it's going to be Q over A over 2 epsilon naught 1 minus Z minus S over R minus Q over A over 2 epsilon naught times 1 minus Z over R. And this reduces to Q over A over 2 epsilon naught S over R. And here's another chance for you to do a little algebra practice. So prove this to yourself. And now let's look at location 1. E also points to the right. So E1 is approximately Q over A over 2 epsilon naught 1 minus Z over R minus Q over A over 2 epsilon naught times 1 minus Z plus S over R. And this is, let's write it on the next page, but let me give you a giant hint. It is the same thing as location 3. Q over A over 2 epsilon naught S over R. All right, so this field, which is outside of the capacitor, this is called the fringe field. And as you can see with having this fraction in it, where you've got very small on top, very big on bottom, this is small compared to the field inside the capacitor. So every once in a while, we will do a calculation where we are going to need that fringe field, but generally speaking, it's something that we'll often neglect. It just depends on the setup. You always have to ask yourself, is this going to contribute a measurable amount? Sometimes yes, sometimes no. So let's look at the units. So inside the capacitor, you have coulombs meters squared over Newton meters squared over Coulomb squared, which is newtons per coulomb, as expected. And let's look at the units of the fringe field. Coulomb meters squared over Newton meters squared over Coulomb squared times meters over meters, which once again reduces to newtons per coulomb. And so let's just quickly recap, as these are important values that we will see quite often, that the field of the capacitor is approximately Q over A over epsilon naught inside, and the fringe field is approximately Q over A over 2 epsilon naught S over R, which is outside. All right, and that wraps up 15.5.